Okay, let's just record it, and I'll accept responsibility if something goes badly wrong after that. Okay, so it's, yeah, so we're recording now, I think, and it should work out okay. It's going to be a bit tappy because of the yep, it's going to be a bit tappy because the pen makes quite a tapping noise, as you can hear there. It's just the way it works. It's just something to get used to. Okay, what's next? What's the next question? What's the next thing someone would like to do?
On slide 20 of the normal slides, you talked about like singlet states or odd functions and things like that. I was just wondering what you meant by that.
Yep, so we go back to slide 20. Just give me a wee second here. It's going to take us. We need to dig our way through the chaff of the Frank Condon factors. Yeah, we're still going. Okay. There we go. This one here, yeah? Hello?
Yeah, that one.
Yep, cool, brilliant. Okay, so basically, I mean, so I think first, are we happy that we understand what we mean by an odd function and an even function? Is everyone pretty happy with that? If you're not, just sing out or just post something in the chat. Okay, well maybe I'll just go over it again just so we're all clear. What it basically means is in an odd function like y is equal to x, if I go minus L, I get a particular answer. In the case of y is equal to x, it would be minus y, right? And then if I go plus L, I get the plus version of that answer, right? So if you imagine y is equal to x, if I go minus 4, then this is also minus 4. So this point is minus 4 minus 4. And if I go plus 4 along here, this is plus 4 here, okay? In the case of y is equal to x squared, that's an even function. So if I go plus 4 this way, this is 16. And if I go minus 4 this way, this is also 16, yeah? So then what do I mean by the odd and even, which all I've done is written this right here, right? And I think I showed this with my hand, so I can't, I'll try it. Yeah, let me try it a different way. So let me just do something here. It's a wee bit cumbersome getting an extra page on here, but I think I can insert a page. Yep, that looks promising. Yep, excellent. So if we just go down, the different software works in different ways. This software is quite good at some things, but quite bad at others. So, so if I just look at those, reproduce that diagram. So we have a LUMO, and we have our ground state like that. So that's the S0 state. And then I've drawn two different, this is the HOMO then. And then I've drawn a state like this. So this is the S1 state. And then I've drawn a state like this, which is the T1 state. Okay. So it's kind of like the idea that we had up here about even and oddness, right? It's kind of like that idea there. So let me just get rid of it. It's kind of like that idea there, okay? Except it's with regard to switching the electrons around. So maybe a way to do this is if I put a tag on the electron, this is a virtual tag, right? We understand. So I just put a tag in each of the electrons down here. And then I switch them around to see what happens. If I switch this one around, if I switch those two around, I end up, so if I just draw it down below after I do the switch, so I'm going to end up with something that looks like this. So I switch my electrons around and you can't tell the difference. I'll move them so that you can kind of tell that they've moved, but it looks the same, right? So S0 looks the same as it did. Or sorry, yeah, it looks, sorry, forgive me. It, up there. Sorry about that. Sorry. So if we take this one and then we move it around, right? So we switch the spins around. Now it's not so obvious in the S0 state because they're in the same orbital, but it's a bit more obvious when you look at the S1 state, because now what happens is the pointing down electron is here and the pointing up electron, which we put the little red tag on, is up here, right? So that's like an odd function, right? Because I multiplied this by -1 to get that, and I multiplied that by -1 to get that, yeah?
Yeah, okay. But
if we look at T1, you see that doesn't happen. So yeah, I switched the electrons around, but you couldn't tell, right? They look exactly the same. And that's the behavior of an even function, because it's like I multiplied that by 1 and I multiplied that by 1. So that's where that concept comes from.
Okay, awesome. Thank you.
Good. That's great. Good, good, good. Excellent. What's next, guys? No, I'll just check the chat. Sorry. Yep. So if anyone's got anything they want to, yep, just holler. I like unmute and say something. That'd be great. I can't believe this is the only problems you have with this course. Yeah. Do you want me to go through a couple of the tutorial questions just for something to do?
Yeah, that sounds great, Keith.
Yeah, okay, yeah.
Could you go through question 2 with the that tungsten complex on the tutorials?
Number 2, yep. Just let me get it. So we've got, so okay, so we're these are the notes I posted earlier. So this is question 1. I think we talked about this, I think, at some length when we had the previous tutorial. It's pretty much, you know, I think it's pretty straightforward, I hope. And often these questions, sorry, I'm just talking about this because it's the thing in front of me. Often these questions, you know, they're very, I don't want to say they're similar, but they kind of are similar, right? You know, I mean, you know, basically, if you understand that delta Q changes and delta Q makes a difference, the Frank-Condon factors, that's the whole basis of Frank-Condon principle, right? And the presence of Frank-Condon factors. So question, okay, so that's that one. Is question 2 you asked for, yeah?
Yeah.
Yep, okay. Yes, this is a sticky enough question. So we've got, there's quite a lot of it here. So let me just, I'm going to have to roll up and down a wee bit because the, so I'll just, but maybe the easiest way to do it would be put in a couple of pages to work with. Okay. So, okay, so we've got these 2 compounds. So I'll just draw them down here. So we've got our facial isomer. We have our meridional isomer. I'll just try and draw it the right way. Sorry. Yep, that's okay. That's great. So you're told in the question they belong to C3V and C2V point groups, and then you're asked to show the symmetry elements for each of the molecules. So if we just come down, so the symmetry elements for C3V are basically E, C3, and sigma V's, right? So that's probably the trickiest one. So maybe we'll do it first, okay? So we're looking for E, 2 C3 and 3 sigma V's, right? So if we have a look at this, it's kind of a bit funny the way it is at the moment. Maybe a better way to draw it's like, oh, sorry, a better way to draw it is like this. You start to realize it's 3-dimensionality. So if I just get rid of these, you know, so these are going back into the page. These guys here are coming out of the page towards you. And then these ones are going back into the page away from you. And what you could do is you could look along this kind of 3 axis here. So we can rotate it around in our minds, so we can just do it. So if we look from this angle here, we can kind of redraw it. It looks a bit funny the way we can redraw it, but you can redraw it like a Fisher projection. And then, so this is the tungsten, right? And if you think about what's going on here, this carbonyl, well, he's going to just stick straight down, right? So let's just stick him straight down. And then this carbonyl, he's kind of sticking up about 120 degrees away. So we can just draw that like that. And then this one's drawn like that. And then the bromines are behind in this fashion here. So it's like a type of Newman projection, although there's not a bond. It's just, this is the tungsten atom in here, right? Okay, so where do we go from there? Well, then I think it's pretty okay. We've kind of got it. So this is one of the sigma V's. This is another sigma V, and this is another sigma V, and that's it pretty much covered, I think. Then you have to worry about the C3. I think it's pretty obvious that's the C3 axis there. That's C13 operation. That's your C3 axis, and that's you done. So that's that one done. And then the other one, also kind of annoying. So maybe the best way to think about it is that there's sort of a plane made by these guys, and there's a plane made by these guys that are at right angles. So if I, again, if I sort of looked along this bond, again, I was looking from here, what would I see? Well, it would just concentrate what we'd see from that bond. There's the tungsten. There's a carbonyl in front of it. I'm just going to ignore that carbonyl. So we've got two carbonyls, one here, one here, two bromines. There and there. So there's also a carbonyl facing you, and there's also a bromine in behind, right? But you get the general idea. So then here we've got, well, there's your C2 axis. That's good. And then you've got two sigma V's. So one of them is here. Sorry, kind of marked up the right from there. One of them is there, and one of them is there. Okay, so that's basically answering that first part of the question. Okay, so we've got that first part of the question done. And then it says determine the reducible symmetry species for the CO ligands vibrational motion for each molecule. Carefully show the vector mapping for the operations of each of the point groups. So this is, yes, a wee bit involved. So let's try it for, I'm just trying to think how easiest to do this. So I think if we take this type of, if we work with this diagram here, we can do it for these guys first, okay? So if we just strip that diagram down to the bits that you need, you basically need, yep, there we go. So we've got one CO here, one CO there, one CO there. Let's call this R1, this R2, and this one over here R3. Okay, that's what we'll call them. And then we've got a bunch of operations. So I just need to, so we're going to have an, let me just change the color here. Sorry, we're going to have E. We're going to have, we've got two C3 operations and then three sigma V operations. So the characters are going to be 3, and then this character is going to be 0, and then this character is going to be 1. So how do I get that? Well, let's just take an example, okay? So if we start with R1, R2, and R3, when we go to E, you can kind of do it like this, okay? If you're trying to do it in an exam, it's quite a good way of showing it, right? Okay, this is going to be R1, this is going to be R2, and this is going to be R3. If we think of C3, so let's just do C13, okay? That's the simplest one to do. So that's one rotation, right? So R1 goes to R2, R2 goes to R3, and R3 goes to R1. Okay, so that's what I mean by the vector mapping. So none of them, so just to be clear, this and this don't agree, this and this don't agree, this and this don't agree, so the character is 0, okay? And then if we take the last example, again, we'll just put sigma V along R1, just to be lazy. You could even draw it in if you wanted to. And that would be R1 stays the same, but R2, let me just flick back to the laser, R2 gets reflected over to R3, and R3 gets reflected back over to R2, okay? So they switch, so this becomes R3, this becomes R2, and the, character is then 1, okay? So let me just go, I have to go back up to look at the character table now. So what we have then is we have 3, 0, 1. And I don't think it takes, I mean, I think you could do this by inspection. If you take this and you add this to it, then you get 3, 0, 0, 1. So this means that the symmetry of the carbonyls is described by A1 plus E. Is that okay?
Yeah, that makes sense.
Yep, no, that's great. Okay, so if we just go on to the other one, so, yep, we're still on number 2, yep. So if we go to the other one, again, I'd be kind of tempted to use this diagram here. So let me just pull, I have to pull this down because I can't easily copy objects. So just, oh no, we've got tons of space here. Let me just make this a bit smaller so I can actually read it properly. So I'll just put it down here. So we've got, basically we've got CO there, we have a CO here. Sorry, they are in front, so they should be coming down like that. Sorry about that. And then we've got bromine here and bromine here. And that's probably enough to work with. You just really need to think about, we'll call this one R2. We'll call this one R3. And then we'll put a wee plus here that indicates this is R1. So that's the carbonyl coming out at you, okay? And then we've got, what have we got there? Well, we've got E, we've got C2, we've got sigma V and sigma V prime. It hasn't specified any sort of axes here, so you can specify them yourself by saying in the plane of the page. Yep, so you can just write that in the exam. It makes it nice and clear to me what you mean, and that's a good idea, I think. And then what happens is we look and see what happens. So R1, R2, and R3. Well, under E, I'll just do the same sort of style again. I'll make this a little bit bigger so it's easier to see. Just give me a second. There we go. So R1 stays where it was, R2 stays where it was, and R3 stay where they are. For C2, R1 stays where it is, but R3 and R2 are reversed, right? So if we just look at that, we're taking this and we're going all the way around there, and the same for the R3. So we're taking the R3, taking this, and we're going all the way around there. But this one, this guy here stays exactly the same. He hasn't changed. Then for the sigma V, we've got two sigma V's. So the one that we're calling sigma V is this one here, right? And so that's going to keep, R1 is going to be reversed. So R1 actually maps to nowhere. So you just put X, it maps to a bromine, right? Don't need to worry too much about it. And then R2 stays where it is, and R3 stays where it is. Okay, sorry, just checking something there. And then sigma, oh no, sorry, I'm being an idiot. I do apologize. Sigma V is all the way through here. Sorry, I got ahead of myself there. So that also includes R1. So they all stay the same. Yeah. Is that clear? And then sigma V is the plane of the page. Oh no, I've got that wrong. Sorry, I'm being stupid. Sorry about that. I do apologize. I'm stupid. Sorry. So sigma V, actually you just draw it as easier. Actually, sigma V prime is there. Sorry about that. And what's going to happen in that particular case is yep, okay, sorry, I have got it right now. I'm just getting my head around it again. And then R3 and R2 are reversed. So yep, the key thing here is that in this plane here, all of the carbonyls lie in it, so they all stay the same. And then in this plane here, only the R1 stays in it, so it's the only one that stays the same. So then when you come to add up things, it's going to be 3, 1, 3, 1. And so if we scootle back up to the character table, we've got 3, 1, 3, 1. And so what we've actually got, I do apologize, I got the axes different from how I had them previously. So I'm sorry about that, but that's what I've done. I've put the sigma XZ and sigma YZ. I've got the two of them mixed up. I do apologize about that. It means that instead of having 2A1 plus B2, what you actually have is you now have 2A1. That's going to be, if you think about it, that's 2, 2, 2, 2. And then what you've got left is 1, minus 1, 1, minus 1. So it's actually B1 in this particular case. But that's only happened because because of the way I defined these two axes. Is everyone okay with that? Or do you want me just to start again and do it the way it's done in purple? Or has everyone got what I'm getting on, what I'm talking about there? Any suggestions, most welcome. Yep, okay. I'm going to assume everyone's following. That's great. Okay, thank you for that. Okay, so that basically deals with, yep, okay. Okay, so we've determined, carefully showed the vector mapping. We've definitely done that. And then it says factorize the reducible into irreducible representations. Well, we kind of could do that with inspection here, okay? I think these are simple enough that you could do it. I don't think that you need to use the character projection operator here. We can use it later on, but I think for this one, it's probably okay. Okay, so then it says, describe the number of bands you would expect to see. Oh my goodness, sorry about that. That's better, sorry about that. Describe the number of bands you would expect to see in the, infrared or Raman spectrum. Briefly justify your reasoning. So this is really what this bit here is about. But it might be a good idea for me just, if it's okay with people, if I just go through how this works for both Raman and infrared spectroscopy. I think it's not a bad idea. It might, you know, it might be a bit obvious to some of you, but I think it's probably okay just to go through it. So if we just think about, if we just deal with infrared spectroscopy first. So what we're really trying to work out is we're trying to work out the symmetry species for this transition, right? Because that's basically the transition we've got, right? We start in the v equals 0 down here, up to v equals 1. Pretty straightforward idea, and that's modulated by the dipole moment operator. So if I knew the symmetry of that, I could tell you if it was going to be symmetry allowed or not. So what this information here has told us, so just to remind you, we had 2A1 plus B1. That's what we got for these guys here. So what does that tell you? Well, that tells you about the symmetry of the normal modes, right? The Q's tells you the symmetry of the normal modes. How are they related to these wave functions? Well, let's just remember the symmetry of 0 is equal to the symmetry of Q times the symmetry of Q. And the reason for that is that the 0th wave function is proportional to e to the minus q squared, okay? And also the symmetry of 1 is equal to the symmetry of Q times the symmetry of Q times the symmetry of Q. That's because one wave function is proportional to Q e to the minus q squared. So that's where that symmetry idea comes from. And then the symmetry of the dipole moment operator is equal to the symmetry of X, the symmetry of Y, and the symmetry of Z, okay? It's a linear operator, so it can't be curved. It's either got to have a component in X, Y, or Z, and there's no sort of other way of doing that. Okay, now we can actually rationalize this a little bit more. I'm going to show you how to rationalize it. You don't have to, but I'm just showing you how you could do it. So if you think about it, the symmetry of 0 is always going to be totally symmetric, yeah? And indeed, if you look at the symmetry of 1, it has to be equal to the symmetry of Q, yes? Because these two bits here are going to give you the totally symmetric wave function. And when you multiply something by the totally symmetric wave function, it still looks like whatever you started with, right? So that being the case, you know that this is for C2V, right? So for C2V, this is just going to be A1. So you know this is going to be equal to A1. This is just going to be equal to the symmetry of Q, right? Which for 2 of the vibrations is A1, but let's not worry about it. So then all we have to do is work out the symmetry of the dipole moment operator, and it's just X, Y, or Z. So let's just scoot up to the character table. And we've got Z, X, and Y, and that's A1, B1, and B2. That's going to be A1, B1, and B2. Okay, and that's the Z. Actually, maybe I'll do it in the right order, sorry. Let's do it as X, Y, and Z. So it's B1 for X, B2 for Y, and A1 for Z. Okay, so that's the X, the Y, and the Z. And I just got that. I literally just got that by reading it off the character table, okay? So just literally reading it off the character table right there, okay? Information's sitting right in front of you, you just need to read it, okay? That's brilliant. Okay, so we've got that. So now we can ask the question, well, okay, so for C2V, we had the oh, whoops, sorry about that. The symmetry of the COs was equal to 2A1 and B1, okay? All right, so let's look at what we've got here. Well, that would mean if we thought about it, if we thought about the A1 modes, okay, their symmetry for 1, mu, 0, you would write like this. So for the 1, it's just the symmetry of Q, so it's just the symmetry of Q. So let's just do it that way. So it's going to be the symmetry of Q, which for an A1 mode is going to be A1. And it's going to be times. Well, then we need to look at the symmetry of the dipole moment operator, right? So I'm just trying to color code these for you. Okay, so we start there, we go to green, and that's going to be B1, B2, or A1. And then the last one we worry about is the symmetry of 0, the vibrational state, the vibrational wave function B is equal to 0, and it's A1. And so we just put that in times A1. Now, we kind of know the answer to this, right? The only way that you can get the thing to be totally symmetric is to multiply A1 by A1 by A1. And you can write, quite reasonably, you can write this leads to A1 symmetry, right? So it's IR allowed in the Z-axis direction. And you know that because it's the Z-axis, this is the Z-axis, right? That allows this integral to be non-zero. So that's kind of the key issue there, right? Okay, that deals with that mode. If we go to the B1 modes, or the B1 mode, sorry, there's only one of them. Then again, we go through exactly the same process. I won't belabor the point, I'll just write down the result. So it's going to be A1, or sorry, forgive me, sorry, it's going to be B1. Sorry about that, times, and then it's going to be B1 times B2 times A1. So that's the symmetry species for the dipole moment operator, and then it's going to be times A1. So this way you can circle your way through here and it's absolutely fine. You just go this way, and that also gives you A1 symmetry. So that means that this transition is allowed, but in the X direction, right? Because it's from the X direction that you got the transition moment integral to be non-zero. So just for completeness, I'll just put this in here. Okay, so that's for those guys. Okay, so that deals with the infrared, right? So we've got the infrared covered. So now we go on to the Raman, and the only real difference here, I mean, we kind of have a lot of the information. So the Raman, it's the same idea. You're now worried about this integral here. And the only thing that's different is the polarizability tensor. And that has the symmetry species equal to x squared, xy, all those good things, right? The binary combinations. So you can again read it off the character table. So for C2V, let's just go and read it off, shall we? For C2V, they're all of them. Every single one of them's alive, right? So you can see you've got x squared, y squared, z squared. They all are A1, totally symmetric. XY, XZ, YZ. Sometimes they appear as combinations, doesn't matter. The symmetries, that's the way to consider the symmetry. Okay, so that means that everyone's allowed. That's what it is. So you've got A1, A2, B1, and B2. I mean, because they're all, I mean, you could kind of take a shortcut because they're all allowed. Because all of the symmetry species, or sorry, because, I should write this better, alpha has symmetry species for all of C2V, all vibrations must be Raman active. That by say Raman active, I mean that they're allowed transitions. So A1, 2A1, and B1 are all allowed. Okay, and that's, or you can go through the process that we did here. Let me just show it to you for one of them, right? Let's just do it for the B1 just to give an example, okay? So if we wrote it for the B1 mode, so for the B1 mode, so it's B1 for the, oh, sorry, I'll do the color coding again. It's quite helpful, I think. So we've got that, and I think this was in green, and then this one's in red. Okay, so that's the color coding we're going to try and use. If I remember, B1 times, and then the polarizability tensor is A1, A2, B1, and B2. And then the final bit is that the B equals 0 has A1 symmetry. So again, if we just slide through with our what's going to work, that's going to work, it's going to be allowed. And here you can't use the phrase, you know, up here we were able to use this, oh, it said it's allowed but in the X direction, it's allowed but in the Z direction. For Raman, it's a little more subtle. It's allowed and it's depolarized. Oh, oops, sorry. And it's depolarized. Okay? And for the A1s, so if I, just for completeness, I will do this. For the A1 mode, it's going to be, again, we'll just go through the process. So it's going to be then A1 times then A1, A2, B1, B2. And that would be just like that. And that's allowed and polarized. Okay, so that's where I'm coming from. I'm just going to check what the chat message was in case it's this one. No, the B1 doesn't correspond to a particular axis. Sorry, that's so. In the case of the, that's a really good question. In the case of the infrared, because it's linear, it's easy to associate the symmetry species with a particular axis. But B1 in this particular case, if we just go up, B1 is associated with XZ, but it's a little bit more complicated than that. I mean, basically, all you can really say is that it's either up here, so it's either totally symmetric or it's not totally symmetric. There is no axis specificity other than totally symmetric and polarized, or not totally symmetric and depolarized. Okay, I hope that answers that question. That's basically so this one here is allowed and polarized because this is the totally symmetric symmetry species. So this is the diagonal parts of the polarizability tensor, and this one's not because it's the off diagonal parts of the polarizability tensor. So, I mean, the issue of polarization is a wee bit more complex in Raman spectroscopy, and I think we really just scratched the surface of it, which is fine. It's totally okay for what we're trying to do. Okay, so let's move on. Let me just...
Can I just ask a question about,
yeah, sure,
when you do the B1 mode for IR,
yes.
why does it go from A1 to B1 for the symmetry of 1?
Oh, yes.
I feel like
sure.
it's an obvious question, but...
No, it's a good question. It's a good question. So it's basically up here. So what we have is that the wave function, you know the wave functions we drew way back when? So if we just draw the wave functions out. Yep, they look kind of like that. Is that?
Yeah.
Yep, sweet. So this one here has this form, e to the minus q squared. Yep?
Yeah.
So the symmetry of it is basically the product of q. The symmetry.
Oh, so it's the wave function thing. So it goes A1, B1. Ah, yeah, okay,
yes,
cool.
yes. And this one's then just q times e to the minus q squared, which is why there are 3 q's in there. Yep.
Yeah, cool.
Sweet.
Awesome.
Excellent.
Thank you.
Lovely. No, that's cool. That's good. I think I'm getting more feedback at this than I would at our live tutorial, I think. I'm just saying. No, it's a good thing. It's not a bad thing. It's not a bad thing. Okay, so I think we've dealt with that for, did we do one of the molecules? You basically do the other the same way. There's not anything very exciting to say there. This question here is actually quite interesting. Describe how you would differentiate these molecules, in their solution phase spectrum. So the way that you would do that is to think, I mean, it's actually, I think, pretty clear. It's not a trick question, it's just to make you think. So if we I just have to find, sorry, just bear with me a second, okay. So the two results, I remember what they are, so I'll just write them down. So for the facial system, the symmetry species of CO was A1 plus A. And for the meridional, it actually turns out everyone's allowed. So the most obvious thing for solution phase differentiation. Okay, so this one, this is 2 bands, or sorry, good grief. Sorry, this has, in the infrared, it has 3 bands. This one has 2. It also has 2 bands in the Raman. This has 3 bands in the Raman. And if you really want to get cute, it's kind of a nice thing to point out. This has 1 fully polarized band. Oh, heavens, sorry about that. Or not fully polarized, I just call it polarized Raman band. And this has 2 polarized Raman. And that's the difference. That's the only real difference between the two of them. So I think, unless I'm very much mistaken, we have answered all of that question. Is that helpful? Has that sort of gone through it pretty clearly? What's next? Oh, no, hold on, I'll just see what these things say. Yep, great, thank you. So what's next, guys? Someone unmute and ask a question. Oh, actually, I've done it all down here. So, sorry, there's a wee bit of I made a bit of a blue there. Sorry about that. I used a different, sorry about that. I used a different, let me just do something to stop something interfering. Used a different axes above. So I got my X's and my Y's mixed up. Okay, so just be careful of that. That's why this gives B2 instead of B1. It doesn't make any real difference to the study. It just means the numbers are aligned a slightly different way. Okay, what's next, guys?
Sorry, I just want to check when you're determining the axes, is it given on the paper, or do you have to?
Yeah, nearly always. I mean, this is a bit. I mean, I'm really sorry. This is a really bad example because it is easier to make it. I guess it depends. I mean, in this particular case, it's kind of your call how to where to draw the axes. It's totally fine. No one's going to get super excited about it. Just realized I misspelled meridional. Sorry, I have to correct that. Sorry about that. Yeah, I mean, in this case, it makes a slight difference in that you get B2 instead of B1. But to be honest with you, if it's really important, I'm probably going to tell you, I'm going to give you the axes so you don't muck it up. Do you know what I mean?
Yeah.
Because otherwise you just, it ends up, half the people do it one way, half the people do it the other way. And it's not super important, but people can get a wee bit worried about stuff like that. So not always, but generally I'll try and give you the axes. Yeah.
Cool, thanks.
So, sorry, with that question, part 5 again, it's literally just stating what you found in part 4, basically.
Yes. I mean, you do actually need to, sorry?
So that just seemed like rather, don't worry, that just seems a little too easy, like that. Just restating your answer from 4.
Well, it requires you, so can I sort of present the question in a slightly different way?
Sure.
So this is mechanical. I have to think about the data that I mechanically produced.
Oh, right.
Do you see what I mean? So there's a slightly different way of thinking about it that I think is legitimate in the sense that, you know, really this is the bit that is actually you interpreting the data.
Rather than just blindly spitting it out.
Okay. Well, I wouldn't say blindly, but yes, rather than perhaps mechanically just going through the process. Yeah. So this is pretty much a mechanical process, right? So you can go through it mechanically, but that doesn't necessarily mean that you grasp what you'll actually see in the spectrum, which is perhaps pretty important, I think. But I do take your point. You kind of have said you kind of have answered the question. I agree. I am not disagreeing with it.
Cool. Thank you.
Yeah. Any other particular juicy questions you want me to have a crack at here?
Could you explain the effect of the solvent on the emission spectrum versus the absorption spectrum again?
Yep. So this is this one here, right? Yeah, at the risk of making a terrible mess, let me just try something here. I just want to, oh no, I don't want to try it. Sorry, I was going to try something fancy there, but then I don't have a laser pointer anymore, so that's fine. Let's just stick with what we've got. Okay, so basically it's, this is a wee bit involved what I have to do here, so just bear with me. It's fantastic. I actually have to save the, like I say, different bits of software are good for various things. So. Right, that's lovely. Okay, so we just come down, give ourselves, maybe just give ourselves a wee bit of space, and I'll just explain it. If I'm lucky here, I should be able to insert this. I'm kind of hopeful, no, maybe not. Oh, kind of, oh, hold on, sorry. This, as I say, it's a little bit, can be a wee bit clumsy sometimes.
You did the right thing there. It just takes a while for the prompt to show up.
Oh, it might do. Yes, you're right. This happened last time to me as well, and it showed up about 5 times. Anyway, in the hope that it eventually will show up. Oh, there we go. Brilliant. Look at that. You're quite right. It did just take a wee bit of time. Marvelous. There we go. And it's enormous for reasons that I can't. Oh, no, yeah, I accidentally clicked it. Oh, no, I've clicked it 3 times. Now it's very exciting. Oh, let's give up on that. Okay, let's just. Yeah, like I say, some things. Oh, so it's got it there actually. So some things are quite good at, and some things it's not quite so good at. So if you imagine in your mind's eye this. So let me just write down 26650. So we've got 26650. Oh, sorry. So that's where we're absorbing, right? And then we're emitting. And I just need to go back up and look at it at 26460. Now these both originate. So if we just think of the sort of simple diagram, S0 V equals 0, right? V double prime equals 0. And we think of S1 V prime equals 0. What we're seeing is we're going, let me just get this right, we're going down with this one, and we're going up with this one, right? And so the question becomes, well, why aren't these in the same place? They're clearly not in the same place, right? So they're not very different. They're, what is it, 190 wave numbers different? Yep, I think that's right. I think it's 190 if I've got my math right. I'm pretty sure I've got the math right. So it's 190 wave numbers different. Okay, so these two are not equivalent. Okay, that's a bit odd. And the reason it actually sort of makes sense if you think about it is what's going on. Let me just, sorry, just out of habit, let me just fix the diagram. There we go. So if we look at why that would occur, if you think about the ground state, so here's the ground state of anthracene. it has a particular value, right? So it has a wee dipole like that. It's not a very big dipole, it's a wee dipole. So the solvent molecules are kind of hanging around, but they're not very interested because it's not a very big dipole, so they kind of organize themselves like that, rather loosely, right? And then I undergo excitation, right? So I go up to here. So a couple of things to appreciate is that I'll try and draw the sphere about the same because the nuclei and the molecule haven't changed, right? But now there's a big dipole, there's a big green dipole, right? Big giant green dipole. Suddenly now what happens is that, well, actually suddenly now what happens is nothing. Everyone's just the same as they were before because no one has time to move because we're in the Franck-Condon regime, right? So if you want to connect it to something else that we've seen, if we think about the Franck-Condon, think about the various Q's and the various E, the energy up the side here, what we've done is we've gone from the S0 state here, and we've gone up to the S1 state there, right? So, but we're in the Franck-Condon state. We're in the Franck-Condon state here. But you'll notice these two, I mean, they're similar, but they're not the same, right? The nuclear coordinates are not exactly the same. The nuclear coordinates do shift a bit. Don't shift very much, but they shift a bit. But what then happens is that you see this shifting of the nuclear coordinates. It's called the thermal relaxation. Nothing else happens. I mean, all that happens is that the molecule, in fact, the molecule does very, very little. It's actually the solvent molecules around it go, oh, we better get ourselves organized now because we have we've got this big dipole moment here. So now suddenly the solvent molecules want to kind of align more like that. So because the solvent field is different, the energy is different, right? So those of you who did 205, I know it's a long time ago, might remember that you can tune energetics with solvent. And it makes sense if you have a big dipole and you've lots of dipole, lots of polar solvent, then it'll lower the energy. And that's what you see here. Okay, so now we're kind of at the bottom of the well here. So we're kind of here now, right? And now we relax. But we relax, but we only get to here. And the reason we only get to here is that those solvent molecules haven't moved, but now the dipole's got really titchy. So this isn't actually very favorable energetically either. So this is kind of a non-equilibrium position, right? And the way to think about it on the diagram I drew of the Franck-Condon factors is we did this. And then we went, oh, hold on, that's not right. I want to slide on back down. Okay, we'll slide on back down. So you've got this sort of reorganization energy at each end of the equation. So this is then going to be the wave number for the absorption. And this is going to be the wave number for the emission. And they're not the same because of solvent relaxation. There's a really nice, I don't know if I put it, it's a wee bit involved, but there's quite a nice book called Fluorescence Spectroscopy, which is an ebook you can get in the library, and there's quite a nice explanation of it in there, although it's quite mathematical because it actually explains the math behind it, but it's perfectly satisfactory what we've got here. So basically we start here, we go up to there, we then relax over to here, we come back to here, and then we relax down to the ground state. And that's the way to think about it in this sort of cartoon way. And the way to think about it in terms of potential energy surfaces I've shown in black just below. So we start here, we go up to there, we relax to here, we come down to there, and then we relax back down again. So that's where that differential between the, absorption and the emission, that's really where that comes from. Okay? Does that make sense?
Yeah, I think so.
Well, I didn't sound very convinced.
Well, in the spectrum, the intensities of the peaks are also slightly different. Is that something we want to talk about?
Oh, you mean this is taller than this?
Yeah.
Yeah, but they're measuring totally different things, right? Because this is the fluorescence intensity, and this is the absorbance intensity. So there's no, you're right, they're not perfect, but I'm not sure you'd expect them to be because you can kind of see the resolution in the absorption spectrum is a bit better than the resolution in the emission spectrum. So I think
okay, that does make sense.
this differential here is not meaningful in any way. not meaningful in any way at all.
Yes, that makes sense. Cool.
I mean, sorry, I need to be careful there. The differential between that and that and that, oh, sorry, why am I doing that? The differential between that and that and that, they are meaningful. They're Frank Condon factors, but comparing one type of experiment with a different type of experiment, yeah, it's not, I wouldn't get all caught up in that. That can happen.
And when you're talking about the horizontal relaxations on that diagram,
the black ones, yes.
Relaxing? Is it relaxing like vibrationally? Or
No.
Is it just relaxation of the solvent molecules? Oh,
it gets complicated actually. It's not really relaxing vibrationally in this case, because in both cases you started in V = 0 and you went to V = 0. So you're not changing. There is no vibrational relaxation here, right? I need to be careful, sorry, of the molecule. But the molecule exists in a solvent field, and the solvent field is what's doing the relaxing. You see the way these like are big, the ears like of a cat, and these look more like the ears of a meerkat, if you know what I mean. This represents.
That's what I thought.
Sorry? Go ahead.
Yeah, that's what I thought was going on.
Yeah, it's the solvent. It's solvent relaxation is the key thing. So you're quite correct. The molecule itself isn't doing a lot of relaxing, but the solvent is. Okay. I'm pretty good for bringing it to a close, guys, if we're all okay with that. Let me just, yeah, I've completely, yeah, we've got it, oh yeah, oh, right, okay. I've remembered how to actually turn things back on again. Yep, okay. Might actually just bring myself back up. Okay, so. Yeah, because we're kind of a bit out of time. Let me just. Okay, so let me just see. I'll just check the chat. Yep. Okay. Oh yeah, you have a 3:05 lab. Sorry about that. Okay, I don't want to keep you from that. So thanks very much for coming. As I say, we've videoed it. So I'll just, we videoed it. So I'll just post that for you later. Okay. So take care, look after yourselves, and I will see you later, okay? So I'll just end the meeting now. Thanks a lot, guys. Bye.
Thanks. Bye.
Bye.